Hi, I'm Greg Williams, Deputy Global Editorial Director of Wired, and I'm absolutely delighted to be joined today by paleoclimatologist Gina Moseley to discuss her work trying to understand Earth's climatic past. Gina, so excited to have you here today. Really keen to get a sense from you. You know, you've explored some of the most remote areas of the Arctic. What can they tell us about climate change in the past, but also in the present?
Hi, Greg. Yeah, that's a fantastic question. So the world is warming up, as we know, and the Arctic is warming up twice as fast as the global average. And so I'm interested in how climate change has affected the Arctic in the past. And that's because over the last few million years, the Earth has naturally had climate, well, since its beginning, it's naturally experienced climate variability. And so we can tap into periods in the past that were naturally warmer than today as a result of the way the Earth was set up relative to the sun, the way it orbited around the sun. And we can get information from those times in the past and learn from that. And then that provides information and it can be used as an analogue for what we could expect to happen in the future in the Arctic. So that's the kind of basic premise of why we look into climate change in the past in the Arctic.
And on these expeditions, you are going to incredibly remote places. You're in northern Greenland. I'm really intrigued and curious to understand what kind of precautions do you take when you are a long way away from any other human beings?
Yeah, these expeditions take several years just to plan and organise, and that's because there's a lot of moving parts, a lot of logistics just to get in place. And on the team, even to start with, I always have a medic. And that's because even the smallest thing can become major in the Arctic. If there's a bad weather window or the helicopter or a plane isn't available, we might be stuck there for 10 days, 2 weeks without being able to get out if something goes wrong. So we learn even how to set up a camp. So the sleeping tents are far away from the cook tent. The tents are always in a line and not in a circle so that if any creature gets into camp, they don't feel caught in the middle of the camp or trapped. Yeah. We have a tripwire which sets off an alarm, and that was used 3 times on the last expedition, I have to say.
What was there? Harmed.
There was an Arctic hare first time.
An Arctic hare?
Huge. Yeah. They are massive.
Yeah.
A musk ox and a wolf.
Wow, okay. What does that feel like to go somewhere where no other human being has been?
It's just a privilege and an honour, and I feel like we really have a duty then to get the most out of that experience. And so I would never like to go in these places and not map them and document them or do anything, you know. So it's important that when my team and I are the first people in there, that we get the most out of that opportunity.
So, Gina, I've seen interviews where you talk about stalactites, stalagmites and flowstones. Can you just talk a little bit about why these are important, please?
So we can study paleoclimatology through a whole bunch of different archives. You can drill a deep sediment from the ocean or a lake. You can drill ice cores. You can look at tree rings, which people might be familiar with as well. And stalagmites and stalactites and flowstones are just another archive that nature provides us with to look at climate in the past. And caves are found all around the world, pretty much, which is one of their advantages, which means that we can access these archives all around the world. And what these samples will show in Greenland is very different to what a sample from Borneo will show, for instance. So this is a great thing about them. Now, a stalactite forms on the ceiling and a stalagmite forms on the ground. So C for ceiling and G for ground, which is a great way of remembering it. And they form from drips of water. And that water has evaporated from an ocean, travelled through the atmosphere, fallen as rain or snow, passed through the vegetation above the cave and the soil. And through that whole journey, it's picked up a chemical signature of the state of the ocean and the atmosphere and the vegetation above the cave at the time it made that journey. And then it deposits a very small amount of calcium carbonate, and this is what makes the stalactite or the stalagmite. And then I come along, or my colleagues come along, and we analyse all the layers, we analyse the chemistry in order to reconstruct that ocean, atmosphere, vegetation record at the time. And a flowstone is essentially the same thing, except that rather than forming from drips of water, it forms from very thin sheets of flowing water. So it's like a carpet that's being laid down. But ultimately, it records information in the same way. And so these stalagmites and flowstones are found all over the world. So we can access this information, all over the world, and then tie it in with the ocean records, the ice core records, the glacier records, and then it builds up a big picture of the climate at the time.
I think everyone watching this will be absolutely fascinated by the fact that you spend so much time underground.
Yeah.
Like, what kind of length of time are you actually underground for, and what's it like to be underground for that long?
Oh, it's amazing. Caves are fantastic places to sleep in. The acoustics are fantastic in a cave, and it's amazing to be underground with a small group of people who you fully trust, and you just build this amazing team in that environment. So it's as much about the team aspect as being in the cave.
So whether you're in Greenland or Mexico or wherever you are in the world, you are collecting samples that in many cases are hundreds of thousands of years old. Like, how do you feel when you pick those objects up? It's the first human being to maybe ever hold them.
Yeah, it's an incredible thing, but I have to say I started to get a little bit blasé about the age of some of the samples. If it's 10,000 years old, again, it's 10,000 years old. And I got a little bit the same way about something that's a few 100,000 years old. But recently we had samples that are 5 million years old and 15 million years old, and that gave me a whole new excitement again.
So let's take that tiny little rock you're holding, and just if you could explain to us, like, you've got this tiny little rock, what fundamentally is the ultimate ambition of your research using these, as you say, tiny little rocks?
My team and I want to know what information it contains about the state of Greenland, that particular region at the time, and then to use that information and connect it to other archives from around the world in order to piece together the mechanisms that make this part of the world drier at this time, this part of the world wetter at this time. And so it's about taking a small piece of a puzzle, connecting it to other pieces in the puzzle, and understanding how the climate system works in a warmer world so that improves the climate models for the future.
So, Gina, you've brought a flowstone with you today. Super intrigued to learn more about it. So, where was it collected? When did you collect it? And most importantly, what have you learned from it?
Yeah. So this is a sample from what we call Cove Cave, because it does have a Greenlandic name as well, but I can't speak Greenlandic very well. It looked like it was in a cove, so that's what we called it. It was collected in 2019 from northeast Greenland. So this comes from 80 degrees north in northeast Greenland. And this particular sample is really interesting. We had a lot of trouble trying to find out how old this was. So we have very standard dating methods that we apply to flowstones and stalagmites. And our standard dating method goes back 650,000 years, and we couldn't get any ages from this one with that one. But very recently, we got ages of 5 million years on this using a different method and a lab in China. So this is 5 million years old. That comes from a period in the Pliocene when carbon dioxide concentrations were similar to today, actually. So it's a very important sample because it's from a time that really resembles the atmosphere that we have today. This kind of track down the middle is where we take samples of oxygen and carbon, and there are 10 samples per millimetre taken from here, and this is our record of vegetation and temperature change as we go through here. And then these bigger holes here are the ones that we use for the dating. And I can't say much more about that at the moment, other than it's 5 million years old. These are really slow growing. There's not a lot of water available in the Arctic. It's actually a polar desert. It's very dry.
Yeah.
There's not a lot of precipitation, not a lot of water available. If we went somewhere like Borneo or China, where it's tropical and there's a lot of rainfall, then these things grow really fast, many millimetres per year. But no, in the Arctic, they grow very, very slow.
And if money was no object, where would you like to go to conduct some kind of dream piece of research?
Greenland.
Greenland, always Greenland.
so much work to do in Greenland and is so untouched in terms of the cave research. It has so much to offer. And in the preparations for the most recent expedition, originally it was based on visiting one cave that was photographed by the US military in the height of the Cold War. And in the height of the Cold War, the military were looking for places to land aircraft in an emergency. And they took a photograph in 1958 from an aeroplane. And this photograph got passed along to the University of Bristol. And then over the years, it made its way down and it got handed to me one evening in a pub, the same photo. And so the whole that particular expedition was based on one cave in North Greenland. And then when it became clear that we were going to this cave in North Greenland that had not been explored, even though it had been known about for 60 years, I started to look further afield. And North Greenland is full of caves, and each one will contain its information, its record of climate change in the past. And so I think there's a huge untouched archive up there, just waiting to be explored.
And obviously going to Greenland, doing the kind of work you do is hugely expensive.
Yeah.
I just wondered if you could talk a little bit about, any form of support that you've received that really have made this work possible.
Yeah. A project like this can't happen without a huge amount of support. And the most recent expedition was partly funded by the Rolex Award for Enterprise. And it's an award that I always had on my mind for, I've known about this cave in North Greenland for a long time. And I always thought the Rolex Awards is the one to try for that project. And I never expected to be successful, but I was. And so that really allowed the last expedition to happen and gave me the confidence in the validation in the work that I'd done previously as well in Greenland. Recently, it really took off with the Rolex Award.
Brilliant. Well, Gina, it's been so great talking to you. Thank you so much for sharing your experiences and your research with us, and may you spend many more days in Greenland.
Yeah, thank you very much, Greg.